Let's take a look. 29 and 47. We can do some more like that. I see. Whoa. Calm down, sir. Okay. 29. Okay. If I'm looking at a problem and I'm not entirely sure where to begin, especially with one where I think I might use U Substitution, I usually begin by making a guess. Like, what could I possibly use for this problem? There's a couple. I could make my U 1 over t. I can make my U 1 over t squared. I can make my U 1 plus 1 over t. I can make my U 1 plus 1 over t cubed. Like, all of these are in the problem. And so I can make one of them my U and kind of see what happens. But remember, my long-term goal is I want one whose derivative is in this problem somewhere. Now, sometimes that's not always obvious. So when I make it my first step, I'm going to convert these to power form. Let's take a look. This integral becomes the integral of 1 plus t to the negative first power cubed times t to the negative second power dt. And now I have to do some quick mental checks. So each one of these now has changed forms. My first one is t to the negative first power. My second one, t to the negative second. 1 plus t to the negative first. And 1 plus t to the negative first cubed. I want to see if any of these have a derivative in this problem. Well, if I start from the top, I strike gold. Because 1 over t, which is t to the negative first power, its derivative would be negative t to the negative second power, using power rules. Remember, you subtract 1 from the power, multiply by the new power. Right? So, sorry, other way around. Multiply by the power and then subtract 1 from the power. So multiply by the negative 1, it becomes negative t, subtract 1 from the power, negative t squared, which is in the problem, right there. But it's not the best choice. It is a good choice, not the best choice. Instead, what I'm going to choose is this one, which has the same derivative, but has more pieces to it, which means it's going to simplify it much farther. Again, the other one does work, just not as nice. So, I take this problem, I make my u equal to 1 plus t to the negative first power. I take the derivative, getting my du, which is negative t to the negative second power, dt. From here, I can just divide the negative over, get negative du, t to the negative second, dt. So, I replace this t to the negative second dt with negative du. I replace the 1 plus t to the negative first with u cubed, and I integrate. Bring the negative out of the front, and now I have a simple integral to do. The integration rule says I add 1 to the power and then divide by the new power. So this becomes negative u to the fourth over 4, or, as my preferred way to write it, negative 1/4 u to the fourth plus c. Because this is indefinite, there are no bounds on it, we have to include our constant of integration c. Last thing, I plug back in u. Again, we're doing a bounded integral. We don't have to take this last step because we avoid that by adjusting everything to be in the new form. So this is unbounded, we can't take that risk. So, negative 1/4, 1 plus t to the negative first to the fourth power plus c. You could argue whether you should switch back the t to the negative first power. I think it's semantic. Not really necessary. It's nice. So the key strategy here is deciding on your U. If you decide on a good U, the problem's pretty straightforward. If you decide on the wrong U, things just get kind of messy.
What's kind of the key to how you write U, or is it just kind of trial and error?
Some of it's trial and error. My recommendation is as follows. Any chance you get, always look to find a U that gets rid of the most things while still having a derivative in the problem. Again, it needs to get rid of as much as possible while still having a derivative in the problem. So while U, this first one, does work, this one has a bigger piece it's getting rid of, so it's better. If I did choose the wrong one and went here first instead, I will still get the solution, but it requires almost twice as much work. Take a look. If I make this use my U, I'd have the integral of 1 plus t to the negative first cubed times t to the negative second dt. If I choose my t to the negative first to be the integral, my du would become negative t to the negative second dt, which again would become negative du t to the negative second dt, which is in the problem. So I replace that t to the negative second dt with negative du, and I get the following. The integral of 1 plus u cubed times negative du. And that's a big problem, because I still can't integrate. I'm now stuck either doing one of a couple things. I could Pascal triangles this out, throw that out, or I'd have to do another U substitution for 1 plus U. Because 1 plus U, let's call it a V substitution. If I do it this way, then dV would be du, which is in the problem. This is, by the way, a common thing. U is the most common one, but you can also do V's, W's. Just avoid X and Y, because, it's already in the problem. Go back. I'll just wish you went over there. All right. 27. We have finding definite integral of pi sine of pi x dx. Let's take a look. 47. Integral pi sine pi x dx. Just like with the previous one, I would begin by making a list of possible du's. Okay, so what can I choose for my u? Well, for clarity, I should always choose a variable. So choosing pi is a terrible idea. It just is, because it's not a variable. So when I do the du, I will get a value of 0, which means my d pi disappears. Remember, it's constant. So choose something with a variable in it. Okay, so what do I have that has variables in it? So pi is a bad choice. Don't choose that. I could choose sine of pi x, or I can also choose what's inside of it, just pi x. I could also choose what's called the arbitrary case, where I just choose, x. But that's really bad. Like that's the second worst on this list. Choosing pi is the worst, because everything disappears. Choosing x is the worst because nothing changes. Okay, so let's talk about each one of these. Let's talk about this first one. If I choose my u is equal to sine of pi x, my du, I'd have to do a chain rule, which is doable. I do the derivative of sine, which is cosine, and then I have to take the derivative of the inside piece, which would be pi. Well, I don't have a cosine in this problem anywhere. So this is probably not the best way to approach this problem. And moreover, if I try to produce a sine in this problem, I'm going to have to try some trig identities, and I'm not guaranteed to make anything better. So this is probably a bad idea. This one, I've already agreed to a bad idea. But what about this one here? U is equal to pi x. Well, if I choose my u equal to pi x, then my du, remember pi is a constant, so it's like 3. The derivative of 3x is 3, or in this case, pi dx, which is in the problem. We have a pi dx right there. So I can do a simple substitution here and figure out my integral. Let's do it. Integral. So my pi and my dx are replaced with du. My sine of pi x, so the pi x is replaced with a u. I end up with sine u du. This is much simpler. I can do this one with just a simple cheat from our list of rules. The integral of sine is negative cosine plus c. Remember, sine's derivative is cosine. Cosine's derivative is negative sine. So if I already have sine, it will produce negative cosine going backwards. From there, remember to put it back in the correct form. I don't want to have something with u in it. I want to have something with x in it, so I go back to this. And where there's a u, I replace with pi x, so it becomes negative cosine pi x plus c. And as with previous problems, I can always double check this using the first fundamental theorem calculus by taking a derivative. Experience does help with this because it makes it easier to spot your u's quickly. And having good, strong derivative skills makes it easier too, because if you make a wrong choice, you can quickly check it. Whereas if your derivative skills are not as good, you'll take the wrong u, you'll spend 5 minutes trying to make it work, and then realize, oh shoot, I should choose a different u. And now I get to restart. Yay. Any other questions? Number 2 from the homework assignment? Number 29 and number 47.
51 and 59.
51 and 59.
Um,
What? I did. They should be on the back of the page. Double check for me. Like the very last page of the assignment should be the solutions. And if not, I can fix that. Okay. Alright, 51. And please verify my solutions, just in case I make a mistake. Alright, 51. Integral of 1 over theta squared cosine 1 over theta d theta. So what?
I said, I know that this is probably an easy problem, but like the theta is always just like.
Okay.
So easy.
So you know what I'm going to do? Look at that. Didn't change anything. Just how it looks. And sometimes that's enough. Okay. So, in this form, by the way, I've been asked in the past, like, what are some things that could be done to maybe make it a little easier for some problems, like some calculus tips and tricks, you know? My big one, for me, that pops up way too often, is recognizing that 1 over t's derivative is negative 1 over t squared. It's easier to see here when it's in power form, but we rarely write it this way. We usually write it this way. And so while this math is easier to do, I'm more likely to spot this math in the problem. Certain log rules we'll talk about next chapter, some of them, like if you learn them the way you're supposed to, it actually makes it harder sometimes because you have to always convert back and forth between a bunch of other rules from non-calculus classes. Or if I learn it like this, this just becomes negative 1 over t squared, then I can see them quicker and find my u's faster. With that in mind, let's look at the problem. What do we think our u's going to be? Yep. And now using this shortcut, my du is negative 1 over x squared. Divide the negative over. So I get negative du equals 1 over x squared dx. Now, I'm going to simplify as I go. The negative is going to come out front. Okay, my x squared dx becomes a negative du. My 1 over x becomes a u. And now I can integrate. The reason I immediately move the negative out front and often move the constant out front to begin with is because I often make the simple mistake of thinking it's a minus sign. The number of times I've done that in my career is too high. And for some people, you would do the opposite. I knew a friend of mine in college, a guy named Andrew Colum, great guy. He would constantly forget any numbers out front. So we'd always leave them inside because he was less likely to make a silly mistake like that, because he was always likely to drop it out front of here because he's used to writing just integral first. So what you might do is put the negative, like instead, like right there.
That's what I'm used to.
Like that works, right? I just get away from the du. That way I have less likely to make a mistake. But again, I know how my brain works, so I know where I'm going to make the most mistakes. Okay, let's integrate. The integral of negative cosine of u du. Negative sine of u plus c. We then substitute back in. In this case, I'll do it once for x, and then again to put it back in theta. If you're going to use this trick, make sure to put it all the way back. All the way back. A trick that my teacher used to show me was to rewrite the original problem here at the end. That way I make sure it's in the right form. My original problem was the integral of 1 over theta squared times cosine of 1 over theta d theta. And so if I write that here, I'm more likely to remember that theta should be present in the entire problem, whereas if I just write u, I might remember to go back to x, but not remember to go all the way back to theta. And again, just a different way of looking at it. This helps to prevent mistakes. So that was 51 and 59. Was that 51?
I think that was just 51.
Okay, well, let's do 59. This one's more fun. I'm glad you chose it. Integral of cotangent squared of x dx. Okay. Here go my lessons. Are there any functions whose derivative is cotangent squared? No? There's one that gives me just cotangent? Okay, what gives me just cotangent? So, what are our thoughts? I mean, nothing in our list is going to get us there. I'll verify that. If I just use the x, I should get it now. Let's see. Nope. Nothing that gives me tangent squared. Sorry, cotangent squared. Wow. What? I could try to like square this out. So let's look at my options for what I could use for my u. I could make my u cotangent of x. I can make my u cotangent squared of x. I can make my u, I guess it's x, but we've already agreed it doesn't do anything. Okay, let's work through the process. If I make it cotangent of x, what happens? I'd have to take the derivative of cotangent of x to determine what du is. If I do that, what's my du going to be? In other words, what's the derivative of cotangent of x? Negative cosecant squared. Which does not appear to be in this problem anywhere. Right? So not looking too good. If I try to do cotangent squared, well, then I have to do the chain rule. So my du becomes 2 cotangent x times negative cosecant squared x. Again, neither of those appear to be in the problem. If I make my ux, well, then I get du equals dx. It doesn't change anything. Okay, maybe I need to be more creative.
Do you want to rewrite this problem?
I think that's a smart move. So how would I rewrite cotangent squared? Go to our trick sheets. We can try that.
Can we convert it to sine and cosine? So we have 1 over.
Could try that as well, right? Yes. I guess you could also do it like with the square on the outside instead of the square on the inside. Where it's sine over cosine squared. Wait, sorry.
1 over.
Yes. We should flip it around, meaning I get cosine on top and sine on bottom. I think that's going to be our best shot. So, okay, let's ask some questions then. If this is our best chance, well, let's ask the question. What do we choose for our u? Because now I have 4 decent options. Cosine, cosine squared, sine, sine squared. I could even do 1 over sine squared. if I wanted to. Because again, I could pull that piece out and make it a separate piece and therefore be able to take it as my u. So let's make our list again. Let's work them one at a time. I can make my u cosine of x. I can make my u cosine squared of x. I can make my u sine of x. I can make my u sine squared of x. And there's some more extreme ones I could try. None of these work. But I'll start here for now. All right? If I make a cosine, let's take a derivative. So I would get du equals dx. Now, you'll notice in the problem, I do not have that because the sign is in the denominator. So this is not looking so good.
Wouldn't you just want to use the sine squared x? Sorry.
I mean, that's the right way to think. Like, we need to start eliminating these possibilities quickly, right? I'm going to do it in order, though. She's going to work ahead. All right, cosine squared x. Its derivative would be du. I have to do the chain rule. So that'd be 2 cosine x sine x dx. Which I don't have any of these three pieces in my problem. I could move the 2 over and solve that piece, but I don't have cosine times sine in the problem. And the sine is in the denominator, not on top, which means this one is also probably a bad choice. Okay, sine. It's cosine. Which looks much better. Want to try it? Or when I'll also look at this one if you want.
Let's try the sine x.
Okay, let's try it. Okay, so I end up with one of my cosines becomes wrapped up in the dx. So I integrate. On the bottom, I'd end up with u squared. On the side, I end up with du. Pulling one of the cosines out to be with the du leaves a single cosine on top.
Would you have to do substitution?
Possibly. I mean, unless there's a way to convert sine of x into something else.
I mean, I'm sure that there is. I don't know what we're talking about.
Okay, so what are we going to substitute? I can't substitute and they're all in the same form. Right now I have one piece is in x and two pieces are in u. So I got to either convert the cosine into sine or convert back, which would negate the entire point of the problem. Do we have a formula, but that's this way, that directly links sine of x to cosine of x anywhere? Okay. Let's look at that end. Not hold on to it. Okay, we still have this last one to try before we have to start going real crazy. What about sine squared? Well, the derivative of sine squared is 2 sine x cosine x. Well, we have the cosine x, but we now have 3 sines, 2 here and 1 there. It looks like none of these work. I need an alternative. Something. Some way I could maybe rewrite this. We already rewrote it once. Maybe we're missing some piece of rewriting it that could be better. Perhaps, maybe, on your trait cheat sheets, you might want to look at one of the Pythagorean identities. Maybe this will be better. So far, everything we tried hasn't worked. I'm not going to guarantee this is going to be better, but it looks better. Alternatively, up here, I think there's a Pythagorean identity that deals with cotangent. So,
This is Horace from last year. Oh, I'm gonna bring it back.
thank you.
I don't think there's anything in there. No problem. Thank you.
Would not do cotangent squared x plus 1 is cosecant squared?
This could become the integral of cosecant squared of x minus 1 dx. From the beginning, we could have rewritten it this way.
Why did you stop us?
You gotta look for them. Like, I can't promise. Like, do you think I saw it right away?
Yeah.
No. No, I did not. My first thought was to jump to here, same as many of you guys thought, and try to fix this. But as soon as I looked at all four of those options, I was like, nope, none of those will work. I got experience. It's not gonna work. So I immediately jumped back and was like, well, I gotta try something else. And the irony is, if you take this problem and solve it by splitting it into two fractions, you'll eventually get right back where we had up there. Just a different way of doing it, okay? Now, why is this form better? Why is the integral of cosecant squared of x minus 1 better? And I think that's the right one, is it? The cosecant squared of x minus 1 is equal to cotangent squared of x? I think the formula has cotangent squared of x plus 1.
Yes, yes.
So I moved the 1 over? Okay, why is this better?
Because the integral of cosecant squared is
Yep. And the integral of 1 is x. This was not a U substitution problem. For Rizzle, my dizzle.
Oh my goodness. We wasted all that time to not even be right.
That's what calculus
We missed
does.
everything.
I can't tell you what the problem is going to do. We have to give it our best chance and say, okay, based on our intuition, what do we feel? Now, I'll be honest with you. If what calculus tends to show, and I said this at the beginning of the year, is calculus is super easy if you have everything before it perfectly memorized. But you still have to make conscious decisions. And so what tends to happen is many of you will consciously choose on a problem to push the problem in a certain direction because it's something you're more comfortable with. People are like, oh, I'm really understanding U substitution, so you start seeing it everywhere. What if I try this U? Ooh. What if I try this way? Ooh. Or you could do something else. Like there's all these rules out there. And the trig substitutions are the hardest ones to predict. Because again, we now have U substitutions that could fix them, or trig identities that could fix them. It's hard to tell. I can't tell you which one's going to happen on a given problem. You have to be fluent in both languages. Now, I told you the truth. When I looked at this problem, I didn't see it either. My goodness, because I love trig, but I don't necessarily want to pull out a bunch of trig identities, and this one is one I'm particularly not familiar with. Like I'm solid on sines and cosines, I'm not as solid on the tangents, cotangents, secants, and cosecants. And so I will typically convert to sines and cosines when I need to, and then work backwards if I have to. But that's because it's me.
See, if I did this by myself, I would go through all of it and just thought I was wrong and then did walk through the process.
Makes you mad. I understand. I really do. I sympathize. Better than that, I empathize. But the only way to get better at it is to try more. And to try out. And to see some things that cause some patterns. And this is the thing I tell my engineering students too. If it's looking like the wrong path, you have to be willing to abandon it at the drop of a hat. And just be like, nope, bad idea, going a different way. This is not a horror movie where you have to blindly keep walking into the house. Okay, if this house looks scary, leave. Try a different path. There are some times where you're going to have a nasty problem and it's nasty because the problem's nasty. But many, many times more often, if the problem looks like it's nasty, something is probably going wrong. I don't mean nasty like, I had to use a trig identity. Oh, that's nasty. No. No. Nasty is when you're sitting there trying out, what do we do? 8 different U's and none of them worked? That's nasty. So we must have made a wrong decision somewhere. Okay? So, I hope this experience was helpful. You're not always going to see which one's the right spot, so you got to be willing to try any. Trig identities, especially, can pop up. Fantastic question to ask, number 59. Any others?
We do 95.
95? Sure.
Like this is probably how it is doing.
Stop saying that. It's a calc problem. If you start thinking of calc problems as an easy one, you're going to scare everybody else.
I think they're all hard, but I mean,
Grading yourself based upon how much I know is a terrible way to grade.
Can you degree in this?
I have 2,
2 degrees in this.
and I still didn't catch that stupid problem.
you're really upset about it, aren't you?
A little bit. I need to remember my table apparently. It's been long enough since we got it.
Is this 95?
Yeah, 95. Sorry, I'll put that right there. Okay. Make sure everyone has instructions before I start. I think I burned by that yesterday. Finally, area of each of these graphs to verify your results. Yay!
There's a graph in front of
To verify the results, so you integrate with the graphing utility instead. Okay. When I look at this problem, I start looking for U's.
Or you might not.
We might not need a U. As we saw, we could try a trig identity if we wanted to, right? Okay. Now, I immediately noticed there's an x over 2. None of my trig identities deal with x over 2. So that's probably a good indication that that's going to be my U. Just letting you know. That's probably a good indication that's going to be my U. Other U's I could try though. Secant of x over 2. And I could even try secant squared of x over 2, but that's the least likely to work out of all of them because you're just taking everything and plugging it in for a U.
It sounds like a good idea.
So let's try this. If my U is equal to x over 2, then my du is equal to 1/2 dx. I move the 1/2 over. I end up with 2 du equals dx. Questions so far? And let us continue. I end up with integral secant squared of u. Now my dx is replaced with 2 du, so I'm going to do du right here and put the 2 out front, like so. Of course. But don't forget my bounds change as well. So what happens to the lower bound? It was originally pi over 2. What's my new lower bound? Pi over 4. Why is it pi over 4?
Pi over 2 over 2.
Yep, you got to plug this number into here to determine the u version of that number. Plug in 2 pi over 3. What do we get for the top value?
No. Is it right?
Simplify.
Oh,
Pi over 3.
simplify. What is her?
Okay? Remember, you always take your bounds and plug them in for x to determine the u version of them. So I plug in pi over 2 into pi over 2 over 2, which gives me the pi over 4. I plug in 2 pi over 3 into 2 pi over 3 over 2, which gives me pi over 3. Which is pi over 3. Okay.
Can't skip a step.
Is there an integral?
Yeah, exactly.
Wait, did you say? Oh, never mind. I'm looking at the wrong part. Sorry. Well, I was looking at your 2 pi over 3 up there, and I was like, wait a minute. Sorry.
Secant squared.
Really threw me off.
It's the integral is tangent.
So secant becomes tangent. The 2 that's out front stays a 2 out front, creating tangent of u defined by pi over 4 and pi over 3.
So then let's just put this in like the top one. Subtracted by the bottom.
Yep, so 2 tangent of pi over 3 minus 2 tangent of pi over 4. Notice the 2 is applied to both of them. I subtract the entire second piece. Okay, so one of these is actually pretty nice. Tangent of pi over 4 is 1. 2 times 1 would be minus 2. This piece is a little trickier. 2 tangent of pi over 3. Tangent of pi over 3 is the square root of 3. So I get 2 square root of 3 minus 2. Woo!
You're gonna be thinking about that problem all day and how
Probably not. I'm teaching how to graph tangent next block, and I'm going to let you know they're going to cry.
that sounds fun.